So I wanted to start today by just going through the methodology for molecular dating or temporal calibration of phylogenies. But I think it's important, an important part of the phylogenetic modelling process that we understand the sort of temporal calibration process, and we get a grasp on the errors associated with the dates that we can affix to any particular nodes. Just a little bit of background about molecular dating. So it sort of dates back to the 1960s, and the sort of real sort of step forward in methodology was the neutral theory, suggesting that molecular substitutions are random in nature, but they accumulate at a relatively constant rate given sufficient time and divergence. We should expect a similar number of these random mutations for, say, sister lineages, and that we should be able to, following this methodology, we should be able to use the molecular divergences to, if they've been following a random pattern at a constant rate, we should be able to use that to date any particular lineage, because we're assuming a constant, or at least a sort of constant random mutation rate over a sufficient period of time should equal out. It's a controversial technique, but very popular. This slide is a little old now, but it just shows you the results of a Web of Science search for phylogeny and molecular clock or dating or something like this. And almost 20 years ago now, there were 20 publications a year. By the mid-2000s, there were hundreds of publications a year, and since then, it's gone through the roof. There are hundreds of publications each year doing temporal calibration of phylogenies. So the theory is that if we're assuming a sort of a relatively constant random mutation rate, when we align the mutational differences on our phylogeny, here we've got two taxa, and here our tree just represents the relationships between them. When we produce our phylogeny, we can basically, on each lineage, we can say this is a base substitution from the ancestral node to this taxon, and from the ancestral node to this taxon. And so each little block here represents a single base substitution. Now, the neutral theory would suggest that when we have this sister species pattern, we should be able to see roughly the same number of mutations on each lineage that allows us to align these two taxa by branch length. Okay. Branch lengths on phylogenies are typically described by the number of substitutions we can see between the terminal state and the ancestral state. Okay. So, if we have a nice constant substitution rate that's equal for each taxa, we should have this sort of pattern where, again, each little block represents a sort of unique substitution for each taxa. Okay? And by just using the number of substitutions as a branch length parameter, we should have each taxa sort of lined up with the number of substitutions being a proxy for the age until the most recent common ancestor. Okay? When we have this nice, neat pattern, all we need to do is to calibrate the tree in some position to say, I know the date of this node, and when we have that date, all of the other dates fall into place, because we have a relative age. When we calibrate, we can convert the relative age into absolute ages. Okay, so this is the sort of a stylized example where we have a fossil that we can identify at this place. So perhaps this plant fossil has the characteristics of all of these daughter species. Okay, so we can positively identify this fossil at this point on our tree. Okay, this fossil is 10 million years old. Therefore, we can sort of count along the substitutions and infer that this divergence happened at 5 million years, and we obviously know that this is today. Okay, so that's the theory. In practice, we don't have such a neat, regular substitution rate, or at least for the majority of the phylogenies that we look at. We have an inconsistency of evolutionary rates. So at some branches we have a faster substitution rate, and in other places we have a shorter substitution rate. Maybe we haven't got a sufficiently large amount of sequence for the random substitutions to sort of wash out to be the same for both lineages. Okay, so the first thing that we want to do when we're dating our phylogenies is to see whether our data conforms to this constant mutation rate, which we term the molecular clock. Okay, so there's a standard methodology that we can do to test whether our molecular data conforms to a molecular clock. And this is really standard stuff. We're not going to go into it now, but I just want to point out that we just make a reasonably good tree. We enforce a molecular clock that is constant rate of substitutions, and then we make the best tree without that constraint, and we compare them to see whether there's a significant difference, and that tells us whether our data conforms to a molecular clock. Now, typically, the majority of analyses that I've done on phylogenies to date them haven't conformed to a molecular clock. So we have something that looks a little bit more like this, where some lineages have a small number of substitutions, and other lineages have a larger number of substitutions. And when this is the case, what we need to do is some rate smoothing, where we assume that here substitutions have happened a little bit faster, and here substitutions have happened a little bit slower. Okay, so what we want is to morph our tree into what's called an ultrametric tree by assuming faster substitution rates, slower substitution rates. There's a whole bunch of different methodologies that you can employ to do this. So starting with very simple methods like local clock, and then there's the sort of intermediate complexity methods of smoothing methods, and then there's the more complicated methods that integrate the rate smoothing with the phylogenetic reconstruction. And I'm just going to touch on these briefly. Local clock methods aren't really used nowadays, but they assume that this part of the tree has one substitution rate, and this part of the tree has another substitution rate, which is a sort of a mild step away from everything having the same substitution rate. And we can think of, biological reasons why one clade might have faster rates than others. Okay. The smoothing methods essentially employ for each lineage a different rate of substitution, but they assign to each possibility a certain cost. So typically it's the difference between this substitution rate and the daughter lineage substitution rate. and you sort of have costs associated with stretching this to this and stretching this to this. Okay, and then you can compare lots of examples and choose the rate change that has the lowest cost. Okay, and there are a number of methods. So non-parametric rate smoothing was the really popular method maybe 10 years ago, but there are some methodological flaws. It's been widely criticised and it's not used as much nowadays. Penalised likelihood is, again, it's Mike Sanderson's sort of follow-on from NPRS that allows more of a variety of rate changes along the tree. Again, this was popular, but is less so now. The main methodology for molecular dating now is integrating the dating process with the phylogenetic reconstruction, and the most popular software is BEAST. You probably know BEAST, people that do phylogenetics. Okay, if you like, it's the Maxent equivalent of phylogenetic dating and reconstruction nowadays, in that it's the software that many people are using. Okay, and it has an advantage in that you're integrating the cost of your rate changes into your phylogenetic reconstruction. So you do one analysis and you get a dating tree, rather than in the past where you've just done a phylogeny, you have a tree that doesn't conform to a clock, you have varying branch lengths, and then you have to do something to that tree. But nowadays it's try and do everything at the same time.